Okay, for this video, we will be discussing some of the applications of energy equation, mainly focus on the uh, measurement of flow and the instruments that we use. The first one would be what we call the Venturi meter, which is a device installed across a pipeline for the purpose of measuring the quantity of fluid flowing a in the line or in the pipe in the pipeline system. No? So here in figure 5.19 is a general illustration of what a venturimeter is. So uh, if you see something like this in the problems or in actual, you are familiar with that. So a venturimeter is composed of three parts, mainly a uh, converging inlet section, the throat, and a diverging outlet section. Okay, so to minimize the losses, the frictional losses, or sorry, to minimize the losses uh, in the venturimeter, it is ideal that the angle of inclination of the sides of the converging and diverging portions of the venturimeter to be at 6 degrees combined. So so that the losses will be minimized. Okay? So sa pag-compute ng or sa paggamit ng Bernoulli energy equation dito sa gantong mga klaseng problem that involves Venturi meters, just take note that although maraming pinapakitang mga formulas doon sa inyong book, they are all derived from the same Bernoulli energy equation. So for this discussion, dun tayo mag-focus sa pag-solve gamit mainly yung Bernoulli energy equation, because sa dami ng mga formulas na pinapakita ng book, madami kayong tatandaan, no? So sa dami ng mga formulas na may encounter nyo pa, mahirap nang matandaan lahat yon. So just an aid and training na din on your part. Gagamit tayo ng Bernoulli energy equation sa pagsosolve instead na i-memorize natin lahat ng mga binibigay ng book natin, no? So dito sa mga ganitong klaseng problems, especially involving yung mga venturimeters and ibang flow measuring instruments, no? Meron tayong tinatawag na theoretical flow and actual flow, no? Dahil nga kasi sa initial conditions hindi na-account yung mga frictional losses, no? Meron tayong tinatawag na theoretical flow kung saan by the term itself, by theory, using the acceptable physical laws, mathematical principles, siya yung um, siya yung theoretical na flow, siya yung flow na makukompute natin. Whereas yung actual flow naman, from the term also itself, actual flow, it is the actual flow, yun yung actual na nangyayari sa tunay na buhay, no? Nagkakaroon ng mga konting differences yung theoretical and actual flow because of the losses along the way, no? Please also take note that if you're computing for theoretical flow, make sure that you're also using the theoretical velocity, no? Because you cannot get the theoretical flow from an actual velocity. So medyo magkakaroon ka ng confusion doon, no? So dapat kapag compute ka ng theoretical flow, you will also use that theoretical velocity, no? And when we apply the Bernoulli energy equation directly on such problems na Venturi meters, take note then, you have to be very careful or at least very particular kung anong klaseng mga velocities yung ginagamit mo. Di ba kasi makikita mo na lang sa Bernoulli energy equation ay velocity. Wala ka naman nakikitang variable na flow doon sa Bernoulli energy equation, just the velocity. So you have to be careful with that, no? When you're using if you're using the actual flow, you will get the actual when you're using the actual velocity, you will get the actual flow. If you're using theoretical velocity, you will get theoretical flow. Otherwise, kapag meron tayong tinatawag na coefficient of discharge, which is denoted by the symbol C, which is simply the ratio, no? Which is the ratio of the actual velocity to the theoretical velocity. No, it's just the ratio of the actual to the theoretical, which usually ranges of around 0.95 to 0.9798 ganyan. So andun lang yung difference, no. Okay? So yung para makuha mo yung actual discharge, you have to multiply the theoretical discharge with this coefficient of discharge. This is actually a correction factor, itong coefficient of discharge na ito. So usually binibigay siya sa problem, minsan yun ang pinapahanap, no? Pero yung mga ganong klaseng problem ay napakadali lang i-solve, lalo na kung kabisado mo naman ang Bernoulli energy equation. Okay? So let's have this example. This is a similar example as the one in the book, in page 219. No? Pero kung mapapansin nyo, yung solutions na ginamit doon is that ginamit nila yung mga binigay sa book. Kumbaga parang nagkaroon na lang sila ng direct substitution. Hindi na sila dumaan from the start ng pag-compute gamit ang Bernoulli energy equation. So we can compare later on, mako-compare natin kung yung magiging sagot ba natin is the same or malapit doon sa mga na-compute nila. Dahil ang gagamitin natin sa pag-solve is yung Bernoulli energy equation. Okay? So let's read the problem. So a 30 cm by 15 cm Venturi meter is installed in a vertical pipe in figure 5.20. The flow is upward through the meter. A differential manometer containing a gauge liquid of specific gravity 1.5 is attached to the base and throat. The deflection being 80 centimeters. Determine the actual flow if the coefficient of discharge is 0.97. So let's try that. So let's write the Bernoulli energy equation from point 1 to point 2. Let's say point 1 is this one, di yata na ilagay. Ito yung point 1, and then yung gitna ng throat is point 2. So let's write the Bernoulli energy equation from point 1 to point 2, since that is the direction of flow. Sabi, that is upward, right? So we have V1 squared over 2G plus P1 over gamma plus Z1. So wala pa tayong accounted na head loss dito, no? Dahil nga meron pa tayo ditong coefficient of discharge, so hindi natin i-account si head loss, no? Ang makukumpute natin dito ay puro theoretical, sorry. So Z1 is equal to V2 squared over 2G plus P2 over gamma plus Z2. Okay. So with this, alam natin that V1 has a value. So meron tayong mako-compute na value ng V1, meron tayong mako-compute na value ng V2. Okay? Meron tayong mako-compute definite na value ng P1 at meron din tayong mako-compute na value ng P2 later on. Pero dahil meron tayo ditong differential manometer, hindi natin talaga pala mako-compute ng eksakto yung P1 and P2. Makukuha natin yung difference nilang dalawa. So definitely meron pa rin naman magagamit natin sila, or hindi sila maging hindrance para makapag-compute tayo ng tamang sagot. Okay? And then Z1 and Z2 is syempre available naman yan. Okay. So let's try. We know that if the datum is through point 1, we know that Z1 is 0 and Z2 is 30 centimeters or 0.3 meters. Okay, so meron na tayong dalawang values. Next, kapag nire-arrange natin ito, lagay natin lahat sa left side ng equation para mapag-combine natin ng common terms. So we have V1 squared, we have V1 squared over 2G minus V2 squared over 2G plus P1 minus P2 over gamma is equal to 0.3 meters. So, i-analyze natin ngayon yung P1 and P2 gamit yung differential manometer. So, ang given dito is that yan, meron tayong drop na X, then 80 centimeters na gauge liquid, and then tataas ulit ng Y distance going to point 1. So, let's try analyzing that. So, let's start with point 1 or point 1 na lang. So, from the pressure at point 1 minus, okay, so dito tayo sa baba para tuloy-tuloy tayo dyan. Analyze natin yung differential manometer. So we have pressure at point 1 minus, plus, kasi bababa tayo, diba? Bababa tayo, so that is so sabi naman is water nagpo-flow, so we have gamma H, so that would be 9.81 kilonewton per cubic meter times the height of drop, which is Y. Then pupunta tayo ron sa kabilang side, that would be 1.5 times 9.81 kilonewton per cubic meter times the height of rise, that is 0.8 meters, minus another water, 9.81 kilonewton per cubic meter times the height of rise, which is equal to X, that is equal to P2. So if we rearrange this expression, we will have P1 minus P2 is equal to, the rest would be on the other side of the equation, that would be 9.81 kilonewton per cubic meter. In-extra ko na lahat para ang mangyayari na lang is negative Y minus 1.5 times 0.8 meters, plus pala yan, then plus X equal to P1 minus P2. So, analyze natin ngayon yung Y tsaka X. We know that 30 plus Y sorry, 0.3 plus Y 0.3 plus Y is equal to 0.8 plus X. So if we have X minus Y, we will have we will have 0.3 minus 0.8, which is then x minus y is equal to negative 0.5 meters. So, kapag kinumbine natin yon, alam natin that x minus y is negative 0.5. So, i-move natin to dito sa gilid as a supporting supporting computation. So, we will have P1 minus P2 is equal to 9.81 kilonewton per cubic meter times 1.5 times 0.8 minus 0.5 meters. So, P1 minus P2 is equal to open natin yung ating calculator. So that would be 9.81 times open parenthesis 1.5 times 0.8 minus 0.5 is equal to 6.867 kPa. Store natin siya sa A. Gagamit pa natin siya mamaya. Okay. So, meron tayong P1 minus P2. Ang kailangan na lang natin ngayon is si V1 and V2. So, paano natin gagawin yan? So, base sa continuity equation, wala namang ibang lumabas sa tubig, no? Wala namang distributary, wala namang tributaries. So, definitely, we know that the flow in Q1 is equal to flow at Q2. So, with that, Q1, alam natin that A1, V1, sorry. A1, V1 is equal to A2, V2. We also know that A1, B1, A1 is the area of cross-sectional area at section 1 that is that is 30 centimeters, no? So that is pi times 0.3 meters squared over 4. V1 is equal to pi times 0.15 meters squared over 4 V2, and we can cancel pi over 4. That gives us the relationship of V1 and V2. So, pwede nating so, ano ba pinapanam sa atin? Determine the actual flow. Okay, so kahit ano naman pala. So, we can have V1 is equal to 0.15 square over 0.3 meters square V2. Now, this is the relationship of V1 and V2. So, simplify natin yan. So, 0.15 squared over 0.3 squared equals to 1/4, which is V1 is equal to 0.25 V2. So, balik tayo dun sa taas. Since alam na natin ang mga values, V1 is 0.25 V2. So, we will have, substitute natin ngayon, yung values. We will get V1, 0.25 V2 squared over 2G minus V2 plus P1 minus P2 is 6.867 kPa over gamma is equal to 0.3 meters. So with this, we can solve for V2. V2 is equal to so we have 0.3 minus alpha A over 9.81 so close natin sa parentheses times 2 times 9.81 divided by 0.25 ulit 0.3 minus alpha A over 9.81 times 2 times 9.81 is equal to tapos di-divide natin lahat sa 0.25 squared minus 1. Sorry, mali yata ako. Ay, tumutan ko pala ito. Naka-square pala ito. Yeah. Then, we'll get the square root. The answer is 2.8933. And since we know that Q is equal to AV, we can say that Q is equal to A2 V2. We will have the value of, store natin to sa B, store na siya sa B. We have A pi times D squared Q. Ang gagamitan is 0.15 kasi V2 tayo. 0.15 squared over 4 A times V. We have A2 V2 equals to 0.0511 cubic meters per second. That is the theoretical flow. No? Theoretical flow yan. So, punta tayo dito sa baba para sa actual flow. Compute for actual flow. QA. So QA is simply CQT. QA is equal to 0.97 times 0.5 0.0511 cubic meter per second. QA is equal to times 0.97, 0.0496 cubic meter per second. That would be the final answer. So if you would compare your answer to the one that is shown in your book, this is quite lengthy, but this is short. Uh, Hindi siya shortcut, no? Pero pares lang siya ng sagot. Isa lang ang kailangan mong tandaan, Bernoulli energy equation lang. Okay? So, yun. Kaya gusto ko talaga i-master nyo yung Bernoulli energy equation. Okay? So, that would be for this Venturi meter problem. So for the next video we will discuss more on about nozzles.